Imagine a world designed for ultimate power, where human oversight was deemed the only possible weak link. This is the story of a technological titan, an RBMK reactor, operating in the heart of the Soviet Union, promising limitless energy, but hiding a fatal, intrinsic flaw. It was April 26, 1986, early morning. The shift was conducting a routine safety test, a crucial experiment meant to prove the plant could still cool itself during a complete power failure. The atmosphere in the control room was thick with tension, oblivious to the fact that they were pushing the reactor far beyond its safe operating limits, ignoring multiple alarm signals designed precisely to prevent catastrophe. The reactor design itself was a bomb waiting for a trigger. At low power, it possessed a dangerous characteristic known as a positive void coefficient. This meant that as the cooling water turned to steam, a natural outcome of overheating, the fission rate didn't slow down. It violently accelerated. At 1:23 a.m., the fateful decision was made to press the AZ5 button, the emergency shutdown switch, known to the operators as SCRAM. But due to another critical flaw, the graphite tips on the control rods, the initial insertion of the rods actually caused a massive momentary spike in reactivity, injecting power instead of shutting it down. In a fraction of a second, reactor number 4 experienced a power surge 100 times greater than its rated output. It was the kinetic equivalent of a massive chemical explosion. The intense steam pressure instantly blew the 1,000-ton reactor lid clean off the building, a devastating physical rupture that exposed the nuclear heart to the open air. Seconds later, a second, more powerful explosion occurred. It was not a nuclear detonation, but a hydrogen explosion triggered by the superheated zirconium reacting with steam. Graphite, fuel, and radioactive debris were hurled hundreds of feet into the night sky, raining down on the surrounding buildings and initiating dozens of devastating fires. The core was now breached. The greatest engineered disaster in human history had begun, releasing an estimated 400 times more radioactive material than the atomic bomb dropped on Hiroshima. The first responders, the fire brigade from Pripyat, arrived quickly. They fought the fire on the reactor's roof, unaware that they were standing in a field emitting lethal doses of radiation. Many of these men absorbed fatal doses within minutes. Their heroism was instinctive, but their sacrifice was based on profound ignorance of the true danger. Initial reports were deliberately downplayed. Soviet officials reported a fire and some damage, completely omitting the fact that the core was gone and the atmosphere was contaminated. In the nearby city of Pripyat, life went on. Children played outside, wedding ceremonies continued, completely unaware of the invisible, deadly poison settling around them. This denial was compounded by the fact that the city's central radiation monitoring posts were simply not designed to register levels this high. They immediately pegged out, reading only safe. It took more than 36 hours for Soviet authorities to admit the scale of the catastrophe, and only after external pressure made the lie unsustainable. The world's first alert did not come from Moscow, but from a nuclear power plant hundreds of miles away in Sweden. Swedish workers found highly radioactive particles on their clothes, tracing the airborne contamination back to its source, forcing the Soviet government to finally issue a terse 4-sentence official statement. The immediate operational challenge was immense: how to stop the fire and contain the radioactive emission without risking a further cataclysm. Thousands of military personnel and civilians, later dubbed Liquidators, were mobilized. They dropped borosilicates, lead, sand, and clay from helicopters directly into the burning core. This action stemmed the intense heat and reduced immediate emissions, but the extreme radiation dosage received by the pilots remains a tragic cost. The evacuation of Pripyat finally began on April 27th, using over 1,000 buses. Residents were told they would be gone for only 3 days, so they left nearly all their belongings behind. The city of Pripyat, meticulously planned and built for the nuclear workers, was instantly transformed into a ghost city, frozen in time and saturated with invisible danger. But the danger was far from over. Beneath the burning wreckage, a new, more horrifying threat was developing, a potential secondary steam explosion. The molten nuclear fuel was burning through the concrete floor, heading towards a massive pool of water in the lower decontamination tanks. If the corium hit that water, the resulting steam explosion would have vaporized the remaining reactor structure, potentially spreading fatal radiation across Central Europe. To prevent this disaster, 3 volunteers, Alexei Ananenko, Valery Bespalov, and Boris Baranov, dove into the flooded corridors. Their mission was to manually open the sluice gates, draining the pool below the core before the molten material reached it. This was an act of profound, world-saving courage. They succeeded. The risk of the massive steam explosion was averted, marking the end of the immediate existential threat to the continent. However, the core was still active, and the fuel mixture, uranium dioxide, zirconium, graphite, and sand, began to melt together into a lava-like substance. This material flowed through pipes and corridors, eventually congealing in the basement, forming the infamous structure known as the elephant's foot. A few months after the meltdown, this formation was still emitting radiation levels of 10,000 roentgens per hour, enough to deliver a fatal dose in less than 60 seconds. The second immediate challenge was subsurface. The molten core was still generating intense heat and threatened to contaminate the groundwater, affecting millions of people. Hundreds of miners were brought in. They worked around the clock, digging a 150-meter tunnel beneath the reactor to install a cooling plate. Working in shifts lasting only a few minutes to limit radiation exposure, these miners successfully stabilized the ground temperature, preventing massive soil contamination. Their efforts were crucial, but like the firemen, many suffered catastrophic health consequences, another layer of silent heroism underpinning the containment effort. Meanwhile, the Soviet Union faced a monumental task, containing the shattered reactor before winter, leading to the creation of the original sarcophagus. The sarcophagus was a rushed, massive concrete and steel structure, built in only 206 days, designed to seal the radiation inside for at least 30 years. The construction required workers to be constantly rotated due to radiation exposure, using custom-designed bulldozers and robots to remove the highly radioactive debris on the roof. The debris clearance was so difficult that many specialized German and Japanese robots failed almost instantly under the intense radiation, melting their electronics. Ultimately, Soviet soldiers had to perform the clearance by hand, working for only 90 seconds at a time to scrape debris off the roof, known as biorobots.
The sarcophagus achieved its goal of rapid containment, but its structural integrity was always questionable, built over unstable, radioactive debris.
The wind carried the radioactive fallout far beyond the immediate blast zone. The cloud first drifted northwest, then changed direction, spreading radioactive isotopes across the globe. Contamination levels were particularly high in northern Scandinavia, Germany, and parts of the UK, forcing governments to issue warnings on local food supplies, particularly milk and mushrooms. The primary radionuclide of concern were iodine-131, cesium-137, and strontium-90, each with varying half-lives and biological pathways. Iodine-131 led to a massive spike in thyroid cancer among children exposed in the immediate area, as the body mistook the radioactive isotope for regular iodine. While immediate deaths were relatively few, the long-term health consequences, the cumulative cancer rates, and the intergenerational effects remain highly contentious and difficult to accurately quantify. Economically, the catastrophe was crippling. The Soviet Union spent billions on containment, compensation, and relocation, expenditures that severely strained an already failing economy. More than 116,000 people were permanently evacuated from the 30-kilometer exclusion zone, losing their homes, livelihoods, and ancestral land overnight. Politically, Chernobyl was a catalyst. The secrecy and denial surrounding the event exposed the deep flaws in the Soviet system. It became a major factor accelerating Mikhail Gorbachev's policies of glasnost, or openness, and perestroika, or restructuring, as the Soviet regime could no longer hide its failures. Globally, the disaster led to a profound reassessment of nuclear energy safety protocols. The RBMK reactor design was universally condemned. International bodies like the IAEA strengthened their oversight, and Western nations began implementing improved training, safety checks, and emergency response procedures. In fact, Chernobyl became the grim textbook example used to fundamentally change engineering and operational philosophy worldwide, moving from reactive maintenance to proactive risk management. Decades later, the environmental paradox of Chernobyl remains fascinating. With humans gone, nature has flourished within the exclusion zone. Elk, wild boars, lynx, and the critically endangered Przewalski's horses have created a unique, accidental nature reserve, demonstrating nature's profound resilience. While there are localized genetic mutations and higher rates of tumors in some animal populations, the overall biodiversity is far higher than before 1986. The long-term danger, however, never fully receded. The hastily constructed sarcophagus began to show signs of structural fatigue and decay almost immediately. The primary risk was collapse, which could release tons of radioactive dust and potentially millions of cubic meters of highly active material trapped inside. This necessitated the largest movable land structure ever built, the New Safe Confinement, or NSC. Funded by international donations and managed by a consortium of over 40 countries, the NSC is an engineering marvel designed to last for at least 100 years. It was constructed adjacent to the old reactor and then carefully slid into place over the decaying sarcophagus in 2016. The arch seals the reactor, not just for containment, but also to allow for the future demolition and removal of the unstable Soviet structure and the fuel residues within. Inside the ruined reactor, the 200 tons of nuclear fuel mixed with corium remain highly hazardous. The cleanup process is complex, dangerous, and measured in decades. In 2021, scientists detected a worrying increase in fission reactions deep within a chamber inaccessible since 1986, indicating that the remaining fuel was not entirely stable. While these spikes are currently monitored and managed, they serve as a stark reminder that Chernobyl is not a historical relic, but an ongoing scientific management challenge. The ultimate decommissioning of the Chernobyl site, including the removal of all remaining fuel and complete site cleanup, is currently projected to finish around the year 2065. Chernobyl stands today as the undisputed touchstone for nuclear safety, teaching us that technological hubris, combined with systemic secrecy, creates catastrophic fragility. It redefined the concept of an acceptable risk, transforming energy policies, international governance, and public perception of radiation. The legacies of the liquidators, the miners, and the scientists who faced the invisible enemy head-on are crucial lessons for any advanced technological civilization. The story of Chernobyl is not just about the dangers of nuclear power, but the essential necessity of transparency, accountability, and humility in the face of immense power. The inherent flaws in the RBMK design were institutional, buried in layers of Soviet bureaucracy and a culture that valued output over safety. Prior to the accident, several safety concerns regarding the graphite tips and the positive void coefficient had been raised, only to be suppressed by central authorities. The operators on shift were operating under outdated, restrictive protocols, trained to believe the reactor was inherently safe, an atomic teapot that could not fail. The test they performed was poorly planned, demanding the simultaneous override of crucial automatic shutdown systems. The decision to continue the test, despite the reactor being dangerously poisoned with xenon-135, built up during the low power period, was the final, critical operational error. Once the AZ5 button was pressed, the catastrophic physics took over, translating human error into geological consequence. The physical scale of the explosion was tremendous, immediately ejecting 50 tons of vaporized fuel and 700 tons of highly radioactive graphite into the atmosphere. The initial fire burned intensely for 10 days, sustained by the highly flammable graphite moderator, which acted as a massive chimney for the radioactive particles. The initial dose rates near the core were so high that they were measured in millions of roentgens per hour, instantly lethal to anyone nearby. The elephant's foot wasn't just highly radioactive. Its structural composition was unique, a solid lava known as Chernobylite, a new mineral synthesized by the disaster. This material represented the transformation of the reactor core into a stable but highly hazardous glass-like substance. The cleanup operations in the most contaminated spots, like the reactor roof, were abbreviated and terrifying. The lead shielding worn by the liquidators was heavy, hot, and largely ineffective against the penetrating gamma and neutron radiation. Many cleanup zones were contaminated with hot particles, microfragments of fuel dust that could cause internal irradiation if inhaled or ingested. The evacuation of the greater contaminated regions, beyond Pripyat, was slower and more chaotic, with residents often receiving contradictory information. The displaced population often carried the burden of stigma and uncertainty, struggling to rebuild lives in new communities while fearing future health crises. The agricultural impact stretched far beyond Ukraine. Sheep in areas of Scotland and Wales were subject to grazing restrictions for decades due to cesium-137 contamination. Cesium-137, with its 30-year half-life, continues to persist in the topsoil and forest systems, recycling into the food chain through fungi and wild game. The effects on human health remain controversial, often divided between the WHO's conservative estimates and higher figures presented by local studies. The only definitive link is the increased rate of thyroid cancer in youth, where thousands of cases have been directly attributable to the radioactive iodine plume. However, the psychological impact, the chronic anxiety known as radiophobia, is arguably the most pervasive and long-lasting health crisis resulting from the disaster. The failure of Chernobyl forced the shutdown of several other RBMK reactors around the world, though some variants continued operating with mandatory safety upgrades. The international financial commitment to the NSC project was unprecedented, showcasing a global realization that nuclear safety is a shared responsibility. The sheer size and complexity of sliding the new safe confinement arch into position required hydraulic expertise previously reserved for oil rigs and massive ship construction. The exclusion zone itself has become a unique laboratory for radiobiology, studying how various flora and fauna adapt to chronic low-dose irradiation. The red forest, where pine trees died instantly from radiation absorption, is now slowly regrowing, though soil contamination remains exceptionally high. Tourists now visit the exclusion zone under strict guided supervision, turning the disaster site into a morbid monument to human fallibility. The Chernobyl power plant site, while decommissioned, still requires thousands of personnel to manage the ongoing storage of radioactive waste and maintain the containment structures. The lessons learned were tragically reinforced decades later by the Fukushima Daiichi accident in 2011, which highlighted the danger of external, natural forces combined with human design weaknesses. Fukushima prompted further global standardization of severe accident management, focusing on passive safety systems and hardened external protection against natural disasters. Chernobyl remains the unparalleled benchmark of catastrophic nuclear disaster, defining the worst-case scenario that must always be accounted for. The long, quiet watch continues. The physical exclusion zone may one day be shrunk, but the historical and psychological exclusion zone is permanent. The immense energy contained within the reactor, once intended to serve humanity, instead became the ultimate symbol of its technological betrayal. The core design failed, but the subsequent courage of the liquidators and the commitment of the international community provided a fragile redemption. Every safety measure, every oversight committee, and every protocol implemented globally since 1986 carries the silent imprint of that fiery night in Ukraine. The world changed, not just because a reactor exploded, but because the explosion ripped apart the curtain of state secrecy, forcing a global reckoning with technological accountability. We are reminded that even the most complex, robust systems are ultimately governed by human decisions, human integrity, and the universal laws of physics. The story demands that we never forget the cost of denial, the weight of heroism, and the enduring challenge of harnessing the fundamental forces of the universe. Beyond the headlines, the meltdown introduced new scientific disciplines, forcing radiochemists and engineers to study materials under conditions previously thought impossible. The extensive contamination mapping served as a template for tracking environmental pollutants and understanding complex atmospheric dispersal patterns. Furthermore, Chernobyl accelerated the discussion around alternative, cleaner energy sources, sparking a global pivot towards renewables in certain regions. The legacy is therefore dual, a warning etched in concrete and steel, and a foundational push towards a more transparent and sustainable future. The zone continues to operate, not as a source of energy, but as a monument to prudence, attracting researchers and scientists worldwide. It proves that even the most destructive events can yield unexpected lessons, and that even in the absence of humanity, life stubbornly finds a way. The story of Chernobyl is far from finished. It demands continuous monitoring, ongoing funding, and a commitment to remembrance. Thank you for exploring this defining moment in history with us. Disclaimer: this video is a historical analysis produced by Beyond Facts Reality. While we strive for accuracy, certain casualty figures and environmental projections related to Chernobyl remain contested and are based on available official and scientific assessments.